A very warm welcome to today's presentation. My name is Sławomir Czarnecki, and today we are going to talk about a topic that's becoming crucial for the future of civil engineering. We'll be talking about reusing, recycling construction demolition waste in terms of brick aggregate in modern construction materials. At first glance, old bricks might seem like wasteless demolition waste, but as you will see, they actually hold massive engineering and ecological potential. This presentation is created as part of the IM4STEM project at Wrocław University of Science and Technology. So let's jump straight into the details. Before we dive into technical details of masonry units itself and brick aggregate, we need to establish a solid foundation and understand the bigger picture. In modern industry and research, we constantly hear the term sustainability. It has become a fundamental principle that guides how we design, build, and manage infrastructure today. However, to truly apply it in engineering, we must first define what it really means beyond just a popular buzzword. In simple terms, sustainability means meeting our present needs without compromising the ability of future generations to meet their own. It forces us to think long term rather than focusing only on immediate gains or short term project goals. When we design a building today, we must consider its impact 50 or even 100 years down the line. That includes how much energy it uses, where its materials come from, and what will happen to those materials when the structure is eventually demolished. Importantly, sustainability is not just about being green or protecting the natural environment. It is a complete holistic framework built on a delicate balance between three distinct pillars. If we ignore any single of these pillars, the entire concept falls apart and the solution becomes impractical. Therefore, true engineering progress requires us to address all three areas simultaneously. Here, you can see those three core pillars: the environmental, the economic, and the social pillar. As engineers, we sometimes fall into the trap of focusing exclusively on technical efficiency or environmental metrics. However, in the real world, a solution cannot survive unless all three aspects work in complete harmony. They are interconnected, and a weakness in one pillar directly undermines the success of the others. To illustrate this, let's consider a real-world scenario. If we develop a material that is environmentally perfect, but it costs 5 times more than traditional options, the market simply will reject it. On the other hand, if we focus purely on economic profit, we risk devastating local ecosystems and running out of natural resources. Finally, a project that lacks social acceptance or community support will quickly run into regulatory and public resistance. That is why we must actively search for the sweet spot right at the intersection of all three spheres. This balance brings us directly to the concept of the circular economy, which is replacing our traditional industrial model. Ever since the Industrial Revolution, humanity has relied on a linear model. We extract raw materials, manufacture products, use them, and then dispose of them in landfills. Today, we know that this linear approach is unsustainable because our planet's resources are finite. The goal of the circular economy is to close this loop by transforming end of life waste back into high value secondary resources. Why the construction sector is such a crucial player in the circular transition? The reason is simple. Construction is literally the foundation of modern human civilization. We build residential homes, commercial towers, bridges, highways, and heavy industrial infrastructure every single day. Because of its sheer scale, the choices made in construction have a massive global ripple effect. What we decide to build with today shapes the environmental landscape for decades. However, this immense scale comes at a heavy environmental price. The construction industry is currently the single largest consumer of natural raw materials worldwide and consumes vast amounts of energy. As you can see below, the sector as well is responsible for over 35% of all solid global waste generation. From initial raw materials extraction to final demolition, we generate a massive amount of construction and demolition waste. Well, our buildings generally consumes enormous amount of natural resources. Instead of letting them accumulating waste at the end and up in landfills, it must become our primary target to recycle them. To address this problem, we need to understand where all this waste actually comes from throughout a building's life cycle. We have to look closely at three main drivers: new construction, aging building stock, and frequent renovations. In new construction, waste is generated right from the start due to material offcuts, damaged deliveries, overordering, and improper storage on site, meaning materials often become trash before a building is even completed. When it comes to aging buildings, time plays a critical role. As structures age, their materials degrade, energy performance drops, and many eventually reach the end of their design life. That makes structural intervention or demolition inevitable. Finally, during renovations, a large amount of functional or semi-functional materials like concrete or old plaster, tiles, joinery, and partitions are stripped out to meet modern aesthetic or efficiency standards. Combined, these three stages continuously feed massive streams of material into our waste management system, which is precisely why targeted recycling is so urgently needed. As we move further along the life cycle, regular maintenance, renovations, and structural modernization generate continuous streams of debris. Buildings undergo major overhauls every 50 years to meet modern standards or update their functionality. During these renovations, large volumes of old plaster, tiles, walls, and structural elements are stripped out. This creates a steady, predictable supply of mixed waste that accumulates continuously across our cities. Finally, at the end of building's lifespan, the demolition phase generates the vast majority of structural waste. Looking at the chart for the European building stock, a huge proportion of our current infrastructure was constructed between 1946 and 1980, or even before Second World War. Many of these structures are now reaching the end of their design life or are energy inefficient. As demolition rates accelerate to make way for new developments, we are faced with millions of tons of waste every year. However, when we overall analyze the composition of solid waste, we find out that construction demolition waste accounts for roughly 30 to 40% of total volume. It's massive quantity that can be replaced or reused in the future. When we inspect further a typical demolition site, you are confronted with highly complex mixture of materials. You will find crushed concrete, glass, scrap metals, timber, plastic insulation, or even gypsum boards. Sorting and separating these mixed streams presents a significant logistical and technical challenge for recycling facilities. Without proper sorting, most of these materials ends up being discarded together in landfills. Now, moving further to the masonry units and the waste bricks itself. To appreciate why this waste is so abundant, we need to look briefly at its rich technological history. Clay brick is one of the oldest manufactured building materials in human history, dating back thousands of years. Ancient civilizations recognized that molding and firing natural clay produced an incredibly durable, weather-resistant block. As a result, brick became the primary structural materials for years for cities across the globe for millennia, until the time the concrete was invented. When we look particularly at the history of construction of masonry systems, it has constantly evolved alongside human technology. We started thousands of years ago with raw natural stones, moved to fired clay bricks, and today we utilize highly engineered novel masonry units designed for high thermal and structural performance. However, throughout all these eras, the core engineering principle of assembling modular units with a binder has remained unchanged. Understanding this technological evolution helps us see how recycled brick aggregates can fit directly into new generation masonry products or other non-structural materials. Well, to understand also why red brick is such a fantastic candidate for recycling, it's due to its fundamental material characteristic. Firstly, the durability. It provides long-lasting performance with minimal maintenance, according to mechanical wear or strength. This means that even after decades of structural service in a building, the ceramic material itself retains most of its original structural integrity. Secondly, fire resistance. Because bricks are synthesized through high temperature firing process during manufacturing, they are inherently non-combustible and can withstand extreme thermal shock without losing structural capacity. Third, maybe the most important in the beginning, uh, 1000 years before, local availability. Historically, clay pits were accessible nearly everywhere, allowing communities to manufacture bricks locally. It minimized transportation emissions and established brick as a primary building material worldwide. Moving further, thermal mass brick structures possesses high heat capacity, allowing them to absorb, store, and slowly release thermal energy, which naturally regulates indoor temperatures and reduces heating and cooling demands. It's very often observed in old churches or other heritage buildings. Finally, simple production. Compared to complex modern synthetic materials, traditional brick manufacturing relies on straightforward processing of abundant natural clay and water, followed by firing. When we combine all these factors, we realize that crushed brick isn't weak organic waste. It is a highly stable, fire-tested, and durable ceramic material that holds enormous potential when repurposed into new enduring composites. Well, but unfortunately, besides this, currently looks what may happen to all brick masonry and its end of life stage. Despite the high material quality of fired clay, current industry practices are still largely inefficient and unsustainable. A massive proportion of brick waste simply ends up in landfills, where it takes up valuable space and contributes to environmental degradation. Even when brick rubble is reused, it is typically directed into low-value applications, such as, for example, backfilling for excavation, terrain leveling, or as a crude substrate layer under roads and parking lots. In engineering terms, this is a clear case of downcycling. We are taking a highly refined, fire-tested, and durable ceramic material and degrading it into cheap ground filler. This approach completely ignores the chemical and mechanical value of the material. Instead of treating crushed brick as a waste burden to be dumped or buried, our goal must be to shift from downcycling to upcycling, reintegrating this secondary raw material into high-performance structural composite. It can be done by using waste brick as aggregates, not always low-graded, but as promising alternative to the natural ones. How we can implement this approach? The process must begin right at the demolition site. With selective dismantling and rigorous material sorting, once separated from contaminants like wood or material or other organics, the brick waste undergoes mechanical processing using heavy crushers and industrial sieves. This allows us to process dirty rubble into clean, well-graded ceramic aggregate, or fine brick powder with precisely controlled particle size. Then we can move further to integrate it into various composites. Now, let's look for potential examples. How we can use them in composites? Well, there are three main types of composites pathways available. First one, cementitious composites, where brick replaces various types of parts of concrete itself. Second, resin-based composites, which offer high strength and rapid curing. And third, plastic matrix composites, which combine recycled polymers with ceramic filler. Each of these paths addresses different engineering needs and opens up new market opportunities. For example, cementitious composites. Since concrete is the most widely used construction material globally, integrated brick aggregate here allows us to absorb massive volumes of waste. By substituting natural virgin aggregates or cement itself with fine brick powder, this path directly lowers the carbon footprint of concrete and seamlessly supports circular construction on a large scale. In case of epoxy composites, this pathway focuses on value creation, turning low-cost crushed brick waste into high-value engineering materials. By using ceramic particles as functional fillers In epoxy matrices, we enhance mechanical performance and enable specialized high-strength structural and repair application maybe as well. And third, plastic composite. Here we achieve a unique synergy by combining two distinct waste streams, recycled polymers and brick aggregate, into a single sustainable material. This yields lightweight, highly durable products that are ideally suited for non-structural, weather-resistant building elements like pavers, outdoor ties, or cladding panels. In short, each system serves a distinct market need, ranging from high-volume structural application to high-performance specialist materials. Starting with cementitious composites. Cementitious composites basically consist of Portland cement, which acts as the main hydraulic binder. Second, different types of aggregates, fine and coarse aggregate. Third, water, which triggers the hydration process. And fourth, chemical admixtures or various other additives, such as super plasticizers to control, for example, workability, water and cement, or other fillers to make the cementitious mixtures denser. Together, all of these ingredients create a sustainable concrete matrix using recycled that can use, for example, recycling other ways, like for example, fly wash on any other. Starting with cement. Of course, each of these materials can be replaced. However, in this particular shape, incorporating recycled ceramic introduces specific physical challenges that must be carefully managed. As you can see from our experimental data that was gathered from the literature, crushed brick has a porous structure which significantly increases the water absorption or water demand of the fresh concrete mix. Connected with the water to cement ratio, it can be seen or observed from the knowledge that the higher water to cement ratio is, the lower is the compressive strength. So in order to do that, very often we use super plasticizers to reduce this water to cement ratio. However, it's not always in terms of sustainability. When we look, for example, on another option, replacing fine natural aggregate with fine brick aggregate, it yields very promising results in terms of, for example, compressive strength. In various compressive strength tests done through the whole world and gathered the results from the literature survey, the fine brick particles sometimes stay at the same level as the reference mixture or sometimes even exhibit in some examples. Although it has to be pointed out that in those cases, lots of mixtures, reference mixtures, were different itself. So these results are only in terms of preliminary studies. Similar, the results are equally encouraging when replacing coarse natural aggregates with crushed brick particles. Although porous ceramic aggregate has a lower individual particle strength than, for example, natural basalt or granite aggregates, properly designed concrete mixtures still achieve high performance. It can be seen that even with 100% of replacement or substitution of natural aggregate, waste aggregate still achieves promising results. It's due to, of course, for other mixtures of cementitious composites. However, such results are inferior towards the fine aggregate, towards the results obtained for fine aggregates. Was reporting only the results when the replacement was done for 1 particular material. Either it was fine aggregate or coarse aggregate. However, combining all of these in chart and also providing the replacement of both of the aggregates with various replacement ratio, it can be seen that unfortunately all of the manner and behavior of the hardened materials is similar, that it decreases the value of compressive strength. However, it provides the possibility, while looking closely at the trend, so still it is possible to design a mixture that meet the requirements of construction materials. Now, let's move to our second innovation path, epoxy-based resin composites. While cementitious matrices are traditional polymer matrices offer unique advantages such as ultra-fast curing, complete water impermeability, and extreme chemical resistance. In this research, we investigated using gross recycled brick aggregate as a structural filler in epoxy. Well, you can observe how it was all done. We used old waste material in terms of bricks, then use it as a coarse aggregate, which lands into the aggregates in the forms especially prepared. Then the liquid mixture is of epoxy resin with hardener is cast into the molds. That finish and results in a dense, highly durable synthetic stone or synthetic material. Furthermore, we subjected these epoxy brick composites to mechanical testing. The performance was outstanding. The flexural strength results demonstrated that the ceramic particles form a very strong mechanical interlock with the polymer matrix. This also results in numbers where the bending tensile strength is much higher than typically for concretes. Furthermore, the compressive strength of these epoxy brick composites exceeded 50 megapascals and sometimes reached even up to 60. This incredible mechanical capacity opens up high-end structural applications. For instance, these materials are ideal for heavy-duty industrial flooring, chemical-resistant linings, structural repair mortars, and high-precision precast elements. It explores combining recycled brick aggregate with recycled thermoplastic polymers, such as polyethylene or acrylonate butene. This approach is particularly exciting because it simultaneously addresses two major global waste problems: the construction demolition waste and post-consumer plastic waste. We are talking about two problematic waste streams and fusing them into a new composite material. The manufacturing process involves compounding shredded plastic with fine brick aggregate at elevated temperatures. The polymer melts and coats the ceramic particles, acting as continuous binding matrix. The temperature is not that high that it's not affected waste brick aggregate at all. Once extruded or compression molded into shape, the composite cools into tough, a water-resistant solid block. Similarly, performed test provides promising results. Looking at the experimental test data, this plastic brick composite exhibits remarkable mechanical characteristics comparing to mortars, for example. Formulation with polyethylene achieved compressive strength exceeding 40 megapascals, and with bending strength up to 30 megapascals, it is much more than for concrete or mortar itself, about 6 times. As we begin to wrap up today's presentation, let's revisit the sustainability triangle we introduced at the very beginning. The ultimate question for any engineering innovation is, does it truly deliver balanced benefits across all three sustainable pillars? We may try to answer these questions, stating that first, demolition brick waste holds immense potential. Its intrinsic fire-resistant durability and high thermal mass make it a prime candidate for circular construction materials rather than simple backfill. Secondly, published research as well demonstrates that there are some promising technical pathways to use waste brick aggregate in various composites, out of each offering unique avenues to absorb ceramic waste. Third, data synthesized from those studies prove that it might be very beneficial to use constructing demolition waste as a filler in various composites. However, whether these upcycled composites can fully meet all structural and long-term durability expectations in real-world application, it still remains an open question. Moving forward, extensive field testing, standardized guidelines, and industrial scaling will be essential to turn these literature-backed possibilities into everyday engineering realities. So, do they meet all expectations? It still remains an open question. And that's all for today. Thank you for your attention. If you have any question, don't bother to ask me.